Hi, welcome back. Today is a very special day in the wind tunnel. It marks the end of Season 1 and the start of a brand new turbine challenge. We're going to be retiring the old generator. Why? Well, a while ago, I received a comment on one of my videos, and to be honest, I kinda took it with a grain of salt. But then someone I trust, Dan, agreed with the comment. We should be measuring the turbine's torque directly, instead of measuring the power coming from the generator. So today, we'll be building and validating a brake dyno for the wind tunnel. These are also known as a prony dyno. I have no idea why they're called that. Someone can probably tell me down in the comments. But from this point on, I'm going to call it a brake dyno. Before we take a look at how the brake dyno works, I think we should pay homage to the old setup. So I've put together a little highlight reel. It kind of looks like I don't know what I'm doing. Anyways, back to the show. Oh, when I said we were retiring the old generator, it's more like a semi-retirement. Like the door greeters at Walmart. Because I can't be bothered to redesign the mount right now. Where's my stick? There's a stick. Sort of. Now let's take a look at how a brake dyno works. And then we'll make one. Luckily for me, it turns out to be pretty simple. And it's exactly what it sounds like. We just need to apply a braking force to our rotating output shaft, and then measure the opposing force from whatever is turning the shaft. In our case, that's a wind turbine. We can then convert that force into torque if we know the length of the lever that we're using to measure the force. And finally, we can measure the RPM of the shaft and translate the torque into instantaneous power in watts. Let's open up our favorite CAD software and... Whoops, I already did it. Here are all the parts. Let's start with the force measurement. We'll do that using a load cell strapped to a ceramic bearing with this 3D printed bearing block. The bearing block has little detents that match the screw holes in the load cell. I did this because I forgot to order the correct fasteners for the load cell. Great. And then that slips onto our output shaft. The load cell is finished. Next is the brake assembly. The brake has thinner areas back here that act like flexures. The servo just slips into this pocket, maybe, and is connected to the brake with this thick metal wire. Maybe you can see now how that works. And this slips over the shaft. And if we tighten it, this is going well. Now, how are we going to connect the brake to the load cell? We're going to do that with this tiny screw and this intentionally oversized hole. This is kind of similar to a floating brake caliper on a disc brake. And that's that fully assembled. Oh, besides this. Because we want the tests to be consistent-ish, the servo is controlled by the wind turbine's test software. When the servo pulls the levers together, it applies a braking force to the shaft. Now, I know exactly what you're thinking. Max, isn't this plastic going to melt from the heat caused by friction? Well, based on the amount of power that the turbines made on the generator, I think the answer is no. The highest output that we saw was 2.3 watts. And let's pretend that we lost 50% of that power somewhere along the way to measuring it. So we would potentially be dissipating about 5 watts over a couple of seconds. I think it might go up a couple of degrees, but nowhere near the melting region for PLA. I hope. I do think the plastic might be a little bit slippery, but we can cross that bridge when we get there. Hi, Future Max here. I'm gonna take over. What past Max doesn't realize is he was trying to be a little bit too clever with integrating the load cell into the brake itself. Because of this offset, he's not going to be able to confidently tell you the length of the lever used to measure the force, and if that changes depending on the direction the turbine is spinning. So I decided to move the load cell in line with the shaft, and I printed a new rigid post for the load cell to bear against. Alright, let's go ahead and get this up on the wind tunnel. Another thing that changed are the bearings. They're now steel bearings instead of ceramic. At some point, I don't know when, the ceramic bearings exploded. First up is Dan's 4-blade torque turbine. It's a drag style turbine. I really like this new dyno. It's very quick. In the time it took me to do 1 test on the old generator, I can do 4 on this new setup. Let's go ahead and take a look at the new display layout before we test another turbine. First up, I've removed anything that had to do with the old generator, volts, current, and so on. I've added force in grams, torque in Newton meters, maximum torque, and we're also tracking at what RPM the turbine produced the most torque and power, as well as the tip speed ratio. Next is the bibi blade by Paul. The jellyfish blade from Moby Obi is up next. Last but definitely not least is a new 2-blade variant of LLoyd's Remkick 7 turbine. This will be the first new turbine that we test on the new setup. Alright, now let's look at the results. First, Dan's 4-blade torque turbine. Previously it had made 1.29 watts. Today it averaged a maximum power over 3 runs of 3.0698 watts, with a peak torque of 0.046 Newton meters at 480 RPM, and an efficiency of 7.16%. Next is Paul's bibi blade. Previously it had made 1.11 watts, and today it averaged 2.0627 watts, with a torque of 0.0203 Newton meters at 676 RPM and an efficiency of 4.7%. Next, we have Mobiobi's jellyfish airfoil. Previously, it had made 1.41 watts, and today it averaged 3.0626 watts, with a torque of 0.0267 Newton meters, around 564 RPM, and an efficiency of 6.47%. And finally, LLoyd's Remkick 7 airfoil. This is the first new design we've tested, so we won't really have anything to compare it to. It averaged 3.2153 watts, with a torque of 0.03 Newton meters at 360 RPM, and an efficiency of 7.3%. I think the fairest way to rank these is by efficiency, so that puts the Remkick 7 in first, the Torque Turbine in second, the Jellyfish in third, and the Bibi blade in fourth overall. All of these results seem reasonable to me, and I think this is probably a more valid test setup. Let me know what you think of the new testing setup, and maybe next time we should see how the #1 turbine from last season performs. If you want to send in your own designs, I'll leave the instructions down in the description as always, along with all of the data from each of the runs. If you like what we did here today, don't forget to give the video a like, and if you don't want to miss out on any of the wind tunnel nonsense, don't forget to subscribe. Okay, thanks. Bye.